Hello and welcome back to CEN 202 Mechanics of Materials. In this unit, we're going to be talking about transverse shear. This is a phenomenon that takes place when a beam is bent. If you take a look here on the left, you can see the shear force that we've looked at so far. That's across the cross section, generally up or down. But keep in mind there are other potential shears. For example, we can have a shear going back into the beam, and this would be considered the transverse shear. We could also potentially have a shear left or right. This is something that we actually don't see happening. We don't really have to worry about it. But this transverse shear is a significant phenomena, and we do need to know how to analyze it and solve for it. Now, these are designed to accompany your Hibbeler text, and if you have not read Chapter 7, I recommend you do, or at least carefully review it before viewing this lecture. Now let's take a look at shear in straight members. Generally, we'll be looking at beams undergoing bending, but keep in mind this phenomena would apply to any type of structural member that would have shear loading on it. In general, what we've talked about so far is this tangential shear stress, right? This is the shear stress that we show in our shear and moment diagrams. It acts along that cross-sectional surface. It's generally a vertical shear force that we're going to see, and we can determine it at any point using a variety of different methods, both graphically and the method of sections, etc. But keep in mind, if you go back and recall what we had talked about when we were talking about the analysis of shear forces in general, at any point, it turns out that the forces perpendicular to the plane, in this case horizontal and vertical, have to be equal. So any place that there is a vertical shear force, there has to also be a horizontal shear force. And that's the one we're going to worry about in this unit. To give you an idea what's happening, let's take a look at two rectangular beams. In this case, they're stacked on top of each other, but they're not connected. So they're free to move relative to each other, but they are supported by these two structures right here. Now, if we place a concentrated load here and a concentrated load here, this is going to put our pair of beams into bending. Now, if we assume this is a frictionless surface here, we can also show that these two beams are going to bend independently of each other. And the fact is, we know they're going to change length. We've already shown in our previous units that the top surface is going to be in compression, the bottom surface is going to be in tension, the side in compression is going to get shorter, the side in tension is going to get longer. If both of these beams in the same way, we're going to get a significant amount of sliding along this surface as the bottom of the top beam expands and the top of the bottom beam shrinks. So they're going to slide past each other. Clearly, friction would resist it to a certain extent, but what would very much resist it is if the beam was a solid piece of material. In this case, that sliding action can't take place because these two ends do have to remain square. And what is replaced by is a series of internal shearing stresses at these various levels within the beam. Now, to visualize this, think of a beam as a stack of horizontal layers. For example, a deck of cards is a good way to visualize that. If you take a deck of cards, for example, when you're shuffling the cards, and you bend them, and you don't hold the ends, the cards are going to slide relative to each other, and each of the cards are going to bend independently. On the other hand, if you had held the two ends and prevented them from sliding, that same deck of cards would almost be impossible to bend because they're going to resist that bending. The same basic thing happens in a solid beam, and what happens is we get a series of horizontal stresses, right, between each horizontal layer or each horizontal plane. Right? These are referred to as horizontal shearing stresses. So if we look at the rare case where a beam is set up so it's only experiencing bending, Well, in those situations, we refer to that as pure bending, and in those cases, we're not going to have any shearing forces. As a result, we're not going to have any vertical shearing stresses or horizontal shearing stresses. But keep in mind that when we derive the bending stress formula, we actually based it on the geometry of pure bending, but we then showed that it could apply to any type of bending condition, a more general case. Now, one important thing to keep in mind is so far when we've been showing our pure bending, we've been showing these very clean distribution lines, and the deformation follows a very straightforward geometry. Keep in mind, if you have a nonlinear shear to strain distribution, then there is the potential for warping to apply. For example, those two ends won't necessarily remain square. Now, this would happen in a very flexible beam material, and generally it's going to be small. When we're dealing with a very rigid material like, say, concrete or steel, it's going to be extremely small, and the amount of warping generally is considered negligible for these analyses. Now, another thing about the shearing stress formula, it's important to realize that it's not based on the deformation geometry, right? Unlike our bending stress formula. And it turns out that we can actually just look at our static equilibrium, and based on those requirements, we can develop our shearing stress formula. Your text goes through that equilibrium analysis in detail, and I recommend you review it. But the key part of this is the shear formula that is derived. And from that force analysis, we can show that there is a relationship for our horizontal stress. That's going to be tau. It's going to be in units of psi or pascals, depending on if we're using English or SI units. And it's going to be directly related to our shear force. Right? Our shear force should be in pounds or newtons. And a value Q that we're going to talk about, you may recall this from talking about our moment of inertia calculations and moment of area calculations. Q is our moment of area. It's described as A prime times A bar prime. We'll talk about that in a minute. But it's the moment of the area either above or below the surface that we're looking at. Because keep in mind, when we're talking about tau, we're talking about the shear at a horizontal surface. We also need the moment of inertia of the entire beam and the beam width. Right? So the beam width is important here, where you notice it's inversely proportional to the beam width. Where we have wider beams, we're generally going to have smaller levels of shear. So how do we go about calculating Q? Well, if we take a look, as we said, Q is going to be the moment of the area. This is the cross-sectional area, and we can either use the area above the point where the shear stress is to be determined or below. It makes no difference. We'll get the same result. And it turns out that if you think about it as what this longitudinal shear stress is sort of holding on to, right? It's the area either above or below that it's sort of locked into. In terms of this, it's a straightforward analysis. We just go through and determine the area, right? And again, we could choose the area above or below. It makes no difference. The results will turn out the same. And then we're looking at y bar, right? This would be A prime, and then y bar prime. This is the distance from the neutral axis of the entire beam, right, at the centroid of the entire beam to the centroid of A bar. Right? So you'd have to determine the centroid and then determine the distance from that neutral axis. Now, it's important to realize the shear formula does have some limitations. We can't use it in all situations. In fact, one of the key aspects of this is when we were developing the shear formula, we're actually calculating the average shear stress. And this is over the width of the beam. So we're looking at the shear force and dividing it by that width. So we are approximating the shear level as a flat shear level and as it being uniformly distributed. The fact is that's not always the case. Turns out that in terms of the distribution of stress, all of the edges tend to be stress concentration points. So we tend to get situations where we have slightly higher levels of stress at the edges of our cross section. This can be particularly problematic, though, if we have very short or flat cross sections. Turns out short or flat cross sections are going to exaggerate this effect, and we can get significantly higher levels of stress at the edges in those situations. So these need to be handled a little bit differently. So keep in mind, you cannot use this stress formula, this shear formula, for short and flat specimens. Another situation that's potentially problematic is our usual stress concentration issues. And that's when we have big changes in the cross section. So for example, when the cross section starts out thin and becomes thicker, or when it becomes thinner, either one of those cases can cause significant stress concentrations that are different from the average. Now, generally we have a situation, particularly with I-beams, where we're going from a thin section to a thick section. And in those situations, these issues are not really a problem. If you recall, thin sections are going to tend to have higher levels of stress. Thick sections are going to have lower levels of stress. So that drop off of the stress level, even though there's a concentration there, tends not to be problematic. So for most of our I-beams, we can use our shear formula without concern. The other place where it can be problematic is if we don't have linear sections, right? What we've been talking about is sort of straight prismatic members, square members, or members that are made up of multiple rectilinear shapes. On the other hand, if we have a tapered section getting wider or narrower, or something that's curved, then our shear formula will not work effectively or not be nearly as accurate. So keep in mind, the shear formula really only applies to beams made up of rectilinear members only. So if we look at the results of a beam analysis using our shear formula, we're going to see that there's a general pattern of results that we can use for most of our analysis, particularly of these prismatic beams. For one thing, it turns out that the shear formula, the shear level that is calculated, is going to vary vertically along the cross section. So as you move up and down the beam, you're going to get different levels of shear. It turns out that in nearly all the cases, the maximum level of shear is going to occur at the neutral axis. So it's going to be highest at the neutral axis, and it's going to drop to 0 at the two surfaces. So generally, that's where we're going to concern ourselves with, because we're usually mostly worried about where our maximum stress level is. If our beam survives that maximum stress level, then the lower levels are going to be perfectly fine. These can be shown in a graphical representation. So for example, here is a rectangular beam, and we'll see that the shear stress is going to vary in a parabolic manner, where it's going to be maximum at the neutral axis and drop to 0 on both sides. Now this is if we have a beam that has a fixed cross section. Remember when we were looking at the stress, it was inversely proportional to the width of the beam. So if we have a beam that varies in width, so for example, this is a simplified I-beam here, we're going to see that the stress is going to vary, again, inversely with the width. So it's going to be high here in the middle, where we have a very thin section, and then as it transitions to these two wider sections, we'll see it's going to step down. And again, the stress is still going to be parabolic, but a much lower level, because in this case, the force is distributed over a much bigger area. By the way, if we go back to that concept that we were just talking about stress concentrations, clearly this has a potential for a stress concentration, but because it is such a step down, it's not something we really need to worry about. Another phenomenon that we need to be able to analyze is a quantity known as shear flow. Shear flow is the magnitude of the shearing force that's taking place inside a beam or any type of built-up member. This is the shear that's taking place along the longitudinal axis of the beam. Right, we just looked at that quantity, and in general this is going to be supported by the material of the beam, except in the situation where we have built-up members, meaning beams made up of a series of components that are fastened together. So for example, if you take a look here on the left, we see an I-beam type beam that has been riveted together. We have another beam here that's been welded together. We have a wooden beam here that's been fastened by nails or screws. And in those situations, that shear flow has to be supported by these fasteners or fastening system. To determine how much shear flow the actual item needs to be able to withstand, we use a quantity known as the shear flow formula. Shear flow formula essentially is to determine how closely spaced we have to put in our fasteners, say our nails or screws, or what type of welds we potentially need to do, or adhesives when we're fabricating these beams. Because the key thing about it is they have to be strong enough to withstand that level of shear. Turns out our shear flow, we use the quantity lowercase q, or the symbol lowercase q. These are going to be in newtons per meter or pounds per inch. Again, it's the shear force per unit length of the beam, right? And it's going to have the internal shear, V, multiplied by Q. Q is our area amount, right? Remember that moment of area that we just talked about, divided by I, where I is our moment of inertia for the entire cross section. Keep in mind Q is for just the portion above or below whatever surface we're looking at. One of the key things that needs to be determined when designing a built-up member is how closely spaced these fasteners need to be. Keep in mind the whole idea of these fasteners is they're close enough together to resist shear flow, right? And keep in mind we use the symbol Q for shear flow because we want these fasteners to hold these components together. So it turns out the spacing S is going to depend upon the shear flow, Q. The higher the shear flow, the closer we need to space these together, and the maximum shearing force of the individual fasteners. In this case, a stronger fastener means we can space them out further apart. By the way, the same basic technique would be used for analyzing a weld. So how strong does the weld need to be? Or to determine what adhesive could be used. Again, we want to determine that it would be strong enough to provide enough resistance to support this shear flow. The other area where shear flow becomes a potential issue is in what we call thin-walled members. And when we're talking about thin-walled members, it generally turns out that most of our structural members, particularly our structural steel members, are going to have very thin walls or thin sections compared to their height or width. So for example, if you take a look here at this I-beam shown on the left, the webs and the flanges are relatively thin compared to the overall height of the beam or the overall width of the beam. Keep in mind, these are the areas that must support that shear flow. So in those situations, we want to make sure they're going to be strong enough to prevent them from, again, being damaged, deforming, etc. So in those situations, it turns out that if we're worried about the shear flow, we're mostly worried about the shear flow parallel to these various walls. Turns out there's small levels of shear that are perpendicular to the walls, but they tend to be extremely small and have very little effect on the overall level of stress in the beam. So we're going to limit our discussion to shear flow components parallel to the walls. And those are going to be places, for example, here when we look at B and C, we see shear potentially between those surfaces. When we look at our web, we're going to see shear again parallel to these various walls. Those are the levels of shear stress that we're going to concern ourselves with. Now, by far the most common type of thin-walled member we're going to be analyzing are the various types of I-beams, and where shear flow is a potential issue is in the flanges and in the webs. The good news is that both of these components have pretty standardized structures, so we're able to develop a set of formulae to analyze these. So for example, if we take a look at the horizontal flanges, those are generally going to be at the top and bottom of our I-beams. It turns out that the shear flow is going to vary linearly, right? This is going to occur with the maximum level actually occurring at the web. And we know that our shear flow is going to be equal to our shear force times our moment of area divided by our moment of inertia for the entire beam. And if we go through, the equation for our moment of area is shown right here, where in our case, d over 2, of course, is not going to change. That's the distance to the web. B over the 2 is not going to change. That's a constant as well, but this distance x is going to change. The farther out we go, the closer it's going to get to B over 2. And actually, when we get to the end, of course, there'll be no shear stress at this surface. Now, this can be simplified so that it's our shear force times our thickness times d, all those are all constants, divided by 2 times I, and then we just look at b over 2, that's our half of our width, minus x, where x is the distance from there. So we can clearly see that as x gets larger, closer to b over 2, it's going to get smaller. As x gets smaller, drops to 0, for example, right here at the where it meets the web, that's where we're going to have the highest level of shear flow. And of course, that's the area where we'd have to concern ourselves with. Similarly, we can look at the vertical section here, the vertical web section, and in this case, it turns out that shear flow is actually going to vary parabolically. This is a somewhat more complicated equation because of the fact that the area and the distances are both changing. That's why we get a parabolic distribution, right? Keep in mind up here, when we talk about the flange, the distance from the neutral axis is not changing. That's constant. That's why we get a nice linear relationship. But down here, because they're both changing, we're going to see that it's going to vary. Keep in mind, it's still going to be proportional to the shear flow and divided by the moment of inertia. It's going to have that issue of the thickness in here as well. But in this case here, we're going to see that it's going to vary between d squared divided by 4 minus y squared. So again, the further you get away from the neutral axis, in this case measured by y, the higher the shear flow is going to be. So this is a relatively simple equation to look at I-beams, and particularly the shear flow in the webs. Unfortunately, we don't have similar equations for all of the various beams we're going to be looking at, but we can summarize our shear flow relationships that can be helpful in terms of analysis. It turns out when we look at any part of the beam that is perpendicular to the direction of shear, right? In this case here, this web of this channel, we're going to see that the shear flow is going to vary linearly with the segment. Again, 0 at the ends, going to a maximum as it gets closer and closer to where it connects to this vertical member. Similarly, if we look at the vertical section in here, in the vertical sections in here, we're going to see that the shear flow is going to vary parabolically, right? So anytime we're dealing with anything that is parallel to the direction of shear, or even at an incline, in fact, we're going to see that, that we're going to have a parabolic distribution. In general, we can look at all of our cross sections and see that shear actually tends to flow around them. So in these cases, we have these closed sections where it turns out it's going to vary linearly here in our horizontal sections, and then become larger and larger in our vertical sections. And of course, it's always going to be maximum at the neutral axis. So at the central axis here, central neutral axis here, neutral axis here, that's where we're going to have our maximum stress value. Keep in mind, of course, we do have to look at stress relative to areas, so you can't just look at the neutral axis and the analysis is going to be good enough. Obviously, if you had different web thicknesses or different flange thicknesses, you'd have to analyze those.